Now we are going to see the question from signals and system given in GATE 2009. So here given that consider a system whose input x of t and output y of t are related by the equation y of t equals integral minus infinity to infinity x of t minus tau h of 2 tau d tau. So here the h of t are given given in figure. Which of the following four properties are possessed by the system? So BIBO stable, that is bounded input gives the bounded output. Causal, the system is causal. Low pass, the system is low pass. And LTA, the system is linear and time invariant. So here we can observe that given h of t in the figure, it is not equals to 0 for t less than 0. We can observe here we have t value, we have some h of t value for t is negative, then h of t not equals to 0 for t less than 0. So we know that if h of t is not equals to 0 for t less than 0, that is non-causal. So we can say the option A is wrong here and option B is also wrong. Then now we will go for checking this option B and option D. So first we will go for checking the option B. We'll go for checking the option B here, option B. So coming to the LTI system, verifying this as LTI system. So given y of t equals to integral minus infinity to infinity x of t minus tau into h of 2 tau d tau. So here in order to check the system is time variant or invariant, we have the condition that the first step is we need to consider the shifted input signal x of t minus t naught, and for this shifted input we need to find the output from the given system. We will represent it, this is with y of t comma t naught. And the second step is we will make the same amount of shift what we taken in the input, we will apply to the output, then we will find y of t minus t naught. This is for the shifted output. The same amount of shift what we considered in the input is applied to the output also. So the output obtained for the shifted input signal, that is y of t comma t naught, is equals to y of t minus t naught. Then we can say the system is time invariant, nothing but the system does not vary with respect to the time, then it is called time invariant system. If the system is varying with respect to the time, that is y of t comma t naught is not equals to y of t minus t naught, then we can call this as a time variant system. Now we need to check this condition. So I am considering that the amount of shift taken in the input is t naught, that is we are introducing the amount of shift t naught into the input, then the output y of t comma t naught is equals to, for the given system, integral minus infinity to infinity x of, given it as x of t minus tau, we are introducing an amount of shift t naught here, then it is h of 2 tau d tau. This is the output for the given shift taken in the input. And now we'll introduce the amount of shift in the output, the same amount of shift in the output, that is y of t minus t naught. So finding the y of t minus t naught here, that is obtained by just replacing the t with t naught in the given system. So that is x of t with t minus t naught. So t minus t naught minus tau and h of 2 tau d tau. So here we can observe that y of t comma t naught is equals to y of t minus t naught. Then we can say this is time invariant system. Then we can say the either of the B and D may correct. Then by verifying the BIBO condition, that is for bounded input and we need to get the bounded output. So here by considering that the input x of t minus tau, that is x of t is bounded, so we know that h of t is already given as some bounded input signal, then h of 2 tau is also becomes bounded with decreasing space on the time axis, that is compressed one. Then this is bounded and h of 2 tau is also bounded, then h of 2 tau is also bounded. The multiplication of these two becomes bounded. Then the integration of some bounded input signal again gives the bounded output only. Then for bounded input signal we are getting the bounded output. Then we verified that the system is time invariant and the system is BIBO. Then we can say the answer B is correct here. So the answer for this is BIBO and linear time invariant. No need to check the linearity here. The conditions are verified, then the answer B is correct.